Welcome to the Deep Dive, the place where we transform complex research into uh, instantly applicable, high-impact knowledge just for you. Today, we are witnessing a huge shift in artificial intelligence. I mean, for decades, AI was abstract, right?
Yeah,
Algorithms in servers, crunching numbers.
stuck in the box.
Exactly. Now, that intelligence is physically manifesting. It's walking, driving, flying right next to us.
It really is the move from the virtual to the embodied, and that's what we're deep diving into today, embodied AI or EAI. To really get this concept, you have to think about the physical part.
Right.
EAI systems, well, they're defined by having a physical form. Robots, autonomous vehicles, drones. They use sensors to take in the real world
Wow.
and actuators to act upon it. So they navigate, make decisions, interact, all based on that real world sensory input.
And our mission here, for you listening, is to quickly unpack the, let's say, complex computer vision techniques and the cutting-edge algorithms powering this revolution. We'll look at the applications, definitely.
Which are fascinating.
Oh, yeah. But crucially, we're also going to dedicate serious time to examining the critical challenges, both technical and ethical, that this shift creates. You should walk away with a thorough, structured understanding of the tech bridging the digital and physical worlds. Okay, so we all encounter what you might call internet AI every day, right? Language models, things sorting our photos. If EAI is just AI with a body, why is that distinction so important? I mean, why isn't the simple factory arm EAI?
That's a great question because the difference is profound. It really challenges the traditional view of cognition, the old mind-body split. EAI insists that intelligence isn't just a brain in a vat, basically. It arises from sensory-motor integration. It's about a continuous dynamic loop, sensing the environment, processing that input, and then acting. And that action changes the environment, which then feeds new sensory data back in.
So it's a constant conversation between the agent and the world,
Exactly. The system and its environment are locked in this kind of learning dance.
which makes the learning process inherently different. Like if I teach a model by feeding it a million static cat pictures, that's one way.
Right.
But if I teach a robot by letting it, I don't know, physically move around a room and maybe knock things over,
Yeah.
that's totally different.
Totally different. That's the contrast with internet AI. It operates under what's called the static data set paradigm. It just consumes massive, often chaotic, randomized piles of curated data. Think satellite photos, endless selfies, text scraped from everywhere. The key is the data is constant between experiments. It's like this huge scrambled buffet, often with no context connecting one piece to the next.
Wait a second, though. If internet AI has access to, like, all the data, wouldn't that scale overcome the randomness? Why is the sequential learning of EAI better for interacting with the world?
Well, scale gives you breadth, absolutely. You learn patterns across vast data, but sequential learning gives you an understanding of cause and effect, of process.
Oh, okay. Consequence.
Right. Embodied AI trains agents, whether virtual or physical, sequentially. They learn by observing, moving, communicating, interacting, just like we do, essentially. It's about building a consistent, coherent view of the world over time, moving past that static snapshot where every data point is disconnected.
Okay, that makes sense. So if that sequential interaction is key, the agent needs incredibly advanced ways to actually see and interpret its surroundings. How do EAI agents handle the flood of visual data from cameras, from sensors?
Yeah, they rely heavily on some really sophisticated computer vision. We can kind of break down the key processes into what I sometimes call the 3 Rs of image processing for EAI.
Okay, the 3 Rs. What's the first one?
The first R is recognition. This is basically assigning digital labels to things. Think facial recognition, or for a robot handler, recognizing moving objects, knowing what something is as it approaches.
Got it. So identifying that moving blob as a person or a forklift. What's the second R?
The second is reconstruction. Now, this is much more complex. It's about generating a full 3D digital model, a whole scene, often from 2D inputs like camera images.
Wow.
Yeah, it involves intricate stuff, combining shading, looking from multiple angles, using depth information, all to build that complete navigable 3D world map the agent needs.
And the final R to sort of map all that out.
That would be reorganization. This is where the raw pixels from the sensors get grouped into structured data, like a blueprint of the scene. Lower-level reorganization finds basic things like corners and edges.
The building block.
Exactly. And then higher-level tasks involve really detailed pixel classification, which brings us straight to segmentation.
Right, segmentation. That sounds like the most granular level, turning an image into almost a detailed instruction manual for the robot. Can you break down the two main types we see in EAI?
Definitely. Segmentation is all about that detailed pixel labeling, and often powerful models like Mask CNN are the foundation. So first you have semantic segmentation. This categorizes every single pixel into a predefined set like car, road, sky. But, and this is key, it pulls all similar objects together. If there are 10 cars in view, semantic segmentation just labels all those pixels as one big car class. It knows what class is there.
It gets to the general concept.
Yes. But then you have instance segmentation, sometimes called instance recognition. This takes that crucial extra step. It distinguishes each individual instance of that class.
Ah, okay.
So those 10 cars are now treated as 10 separate distinct entities, car 1, car 2, car 3, and so on. For a robot that needs to pick up, say, one specific bolt from a bin of identical bolts, that distinction is absolutely vital.
That level of detail must be indispensable when you move from standard 2D images to 3D data, like point clouds, maybe from LiDAR sensors. I understand standard CNNs, convolutional neural networks, which are great for flight image grids. They kind of struggle with that kind of...
Oh, they completely fall apart. Point cloud data is amazing. For EAI, it's this huge collection of coordinates, X, Y, Z, sometimes color, intensity. It retains incredible spatial depth. Perfect for navigation, but messy.
Very messy. It's sparse, it's high-dimensional, it's not in a neat grid. Standard CNNs just weren't built for it.
So we needed a specialized way to handle that. What was the breakthrough?
The big one was kernel point convolution, or KPC. KPC basically redesigned convolutions specifically for this point cloud structure. Instead of a square kernel, it convolutes around a portion of the point cloud using roughly 7 kernel points spread out uniformly in a kind of sphere.
Huh, interesting.
It means the system can finally effectively process that spatially defined but geometrically irregular 3D data.
And the impact of that technical fix is massive, right? It lets autonomous agents move out of controlled labs and into complex, cluttered, real-world spaces, a messy warehouse, an uneven construction site.
Precisely. It really unlocked the potential of LiDAR and other 3D sensors for mobile agents. And beyond these specific vision techniques, we also just see sheer scale playing a huge role now.
Right. I mean, look at CLIP, contrastive language image pre-training. It was trained on something like 400 million image-text pairs from the web. Compare that to traditional data sets like MS-Sukuko, maybe 100,000 samples. The scale is just monumental.
Orders of magnitude difference. And architecturally, fixing fundamental limits was key too. You mentioned ResNet earlier.
Yeah, ResNet, residual neural networks. That addressed a really... Think of it like trying to shout instructions down a really, really long tunnel.
Okay.
In older, very deep networks, the learning signal, the gradient would just fade out before it got back to the early layers to make adjustments. ResNet found a clever way around this, allowing people to build CNNs with thousands of layers that dramatically cut error rates and enabled the really deep, sophisticated models we see today.
So we have this powerful toolkit, KPC for 3D, detailed segmentation, massive scale, deep architectures. How does EAI translate all that into tangible results out in the world? Let's dive into where this is actually being used.
Okay, yeah. We see really rapid adoption in 3 core areas, I'd say. First, obviously, autonomous vehicles and drones.
Right, the big one.
EAI makes 2 key navigation functions possible here. Visual odometry, VO, that's estimating how far you've traveled just by looking using cameras, and localization, figuring out your precise position relative to a map or known landmarks. Both are absolutely essential for planning your path and navigating safely in real time.
And for things flying overhead, drones.
Drones heavily leverage deep CNNs. They're trained on huge data sets of annotated photos to detect and track all sorts of objects, power lines, buildings, terrain, even wildlife like whales from the air.
Wow.
This allows for really sophisticated obstacle avoidance and autonomous flight paths, crucial for things like infrastructure inspection or deliveries. Plus, we're even seeing end-to-end trained deep CNNs that map camera input directly to steering commands, basically teaching a car to drive by just watching.
That's incredible. Okay, so that's mobility. What about environments where it's all about precision and maybe repetition, like manufacturing?
Right. In manufacturing and quality control, EAI vision systems are transforming factories. They enable collaborative robots working alongside humans and much more flexible automation. AI systems can perform real-time quality control, analyzing visual data, looking for tiny defects in patterns, shapes, colors.
More reliably than humans.
Potentially, yes, especially over long periods.
Huh.
They provide consistent, objective criteria. Think about a human inspector fatigue sets in, attention wavers over an 8-hour shift. An AI system offers uniform quality checks 247, significantly reducing errors associated with human factors.
That consistency is huge. And finally, a field where precision is literally life or death. Medicine.
Absolutely. The integration of EAI into healthcare and medical robotics is truly transformative. You have systems like the Da Vinci surgical robot.
Where to that?
It uses EAI to translate a surgeon's larger hand movements into incredibly precise micro movements inside the patient for minimally invasive procedures. It filters out natural human tremor, enhancing precision and stability. Beyond surgery itself, AI assists in image-guided procedures, analyzing scans in real time, and even in objectively assessing a surgeon's skill during training. And on the therapeutic side, you have embodied assistive robots, exoskeletons helping people walk again, or socially interactive robots used in cognitive rehab therapy.
The technical sophistication is just undeniable. But we absolutely need to pivot now to the hurdles. What are the major challenges, the trade-offs that EAI developers are constantly grappling with?
Yeah, there are significant ones. Technically, probably the biggest persistent issue is the sim-to-real gap.
Seem to real. Okay.
It's this frustrating discrepancy. Behaviors learn perfectly well in a controlled, clean, simulated 3D environment, which is great for safe, cheap initial training, often don't generalize well to the messy, unpredictable real world.
Right. The physics aren't quite right, or the sensors behave differently.
Exactly. A robot might stack blocks flawlessly in the simulator, but then in reality, friction is different, lighting changes, its sensors have noise, and it fails. Bridging that gap is a huge area of research.
The real world is just messy. What about the physical limits of the robots or drones themselves?
That leads straight into hardware and power constraints. For any mobile agent, a warehouse bot, a delivery drone, you're facing critical trade-offs. You need serious processing power for real-time decisions, but that compute has to fit into a small, lightweight package. And crucially, it has to be incredibly energy efficient. Battery life is paramount. You can't have a drone that runs out of juice after 10 minutes. So developers are constantly pushing for leaner, more efficient computation.
And all these agents, they don't operate in isolation, right? Connectivity must be vital for them to coordinate or get updates.
Absolutely vital. The need for high-speed, ultra-reliable communication can't be overstated. For EAI systems to make near-instantaneous decisions in dynamic situations, especially when coordinating, they need ultra-low latency and high bandwidth. This is where things like robust 5G networks become really critical infrastructure.
Okay, so technical challenges are huge. But when we shift to the operational side, the societal layer, we have to talk about accountability, right? Especially since these things are physically interacting with us now.
That's a major concern, yes. It brings up serious issues around transparency and understanding why a system made a decision. Deep learning models, especially in EAI, are often black boxes.
Right.
It's notoriously hard to trace back how a specific critical decision was reached, like why did the self-driving car swerve left instead of right? This lack of clarity really undermines accountability if something goes wrong. We desperately need explainable AI, XAI, built in from the start, not tacked on later, so we can debug, verify, and trust these physical systems.
And thinking about, say, a factory floor or a logistics hub packed with sensors and robots, introducing all that smart tech must raise concerns about monitoring and privacy.
You're absolutely right. Integrating sensors and cameras everywhere for optimal EAI performance inevitably raises concerns about continuous employee monitoring and individual privacy. The very data needed to make the robot's efficient sensor logs, movement tracking can easily become surveillance data. Furthermore, because EAI operates these cyber-physical systems, think Industry 4.0, 5.0, a security breach isn't just about data loss. It has immediate physical consequences.
That's a critical difference. A cyber attack on a website is bad, but an attack on a robotic factory floor.
Exactly. It can cause immediate equipment malfunction, create serious physical safety hazards, or even allow hostile takeover of physical systems. Robust cybersecurity isn't optional. It requires continuous monitoring, strong encryption, solid authentication protocols, everything needed to prevent physical harm from a digital intrusion.
Wow. This has been an incredibly comprehensive look at embodied AI. We've gone from, KPC algorithms decoding 3D point clouds and solving vanishing gradients, all the way to autonomous surgical robots and the critical need for 5G. It's really clear EAI is rapidly closing that gap between abstract digital AI wins and practical, reliable physical action.
It really is. And building on that idea of visual sophistication, maybe a final thought for you to consider revolves around a very specific technique. Metric learning, particularly its use in pose-based facial recognition, this is being explored for high-stakes applications like law enforcement.
Metric learning. Okay, what does that do specifically in facial recognition?
Well, metric learning is a specialized approach. It's designed to teach the system to learn highly discriminative features that essentially ignore or normalize variations in things like head pose, lighting conditions, facial expression.
So it could look at two really different photos of the same person. Maybe one's a clear photo, the other is a blurry, angled shot from a security camera, and still figure out it's likely the same individual, despite the visual differences.
That's precisely the goal. It aims to identify similarities even under extremely challenging real-world conditions where the images look very different superficially. It's an incredibly powerful capability, truly showing how far computer vision has come in dealing with noise and variation.
Okay.
But it fundamentally raises crucial questions, doesn't it? About the necessary levels of transparency and accountability when such powerful, potentially life-altering identification systems are deployed. How do we ensure they are fair, accurate, and auditable?
Yeah, it really forces us to grapple with the implications of machines that don't just process data, but physically experience the world, learn from it sequentially, and act within it. That fundamentally changes the landscape for future human-AI collaboration, doesn't it?
It absolutely does. It's a powerful thought to keep in mind as these technologies become more and more integrated into our daily lives.
Well, thank you for diving deep into all this material with us today. It's been fascinating.
My pleasure. Always enjoy the discussion.